So let's start talking about those periodic trends. So the chemical and physical properties of elements depend on the electrons that they have, which is what we talked about in our previous lesson, how the periodic table was set up based off of the atomic number and the electron configurations that the elements had, and how we saw that law of octaves, or 8, where there were just similar properties in specific elements that varied by 8 electrons. So while we discuss these trends, it's helpful to think of the atom with its electrons in shells orbiting the nucleus, which is how we have been thinking about the atom so far. So we've shown this many times, where we have our nucleus here in the middle, and then we have these shells that go around it. It's going to be very useful to think of the electrons this way. So remember, our electrons are then just our little dots here and here, all throughout those shells. Okay, and we have to remember that n is the shell number that the electrons are housed in. So with each new n, there is a new shell. So this would be n equals 1, that's closest to our nucleus. N equals 2, which is 1 further away. N equals 3, and so on and so on. It goes further and further as you go further out and have more electrons. So I'm just going to copy this in case we need it again in one of our slides. Okay, so the first thing we want to talk about is the radius of each atom. So the atomic radius increases from top to bottom down a group. So let's look at one of our groups here in our image. So here's group 1. So I'm going to start with group 1. And we see that the radius of these atoms, okay, increases as we go down the group. So we see that increasing ionic radius goes down a column, okay, and that's because with each new shell, so here we go from n equals 1 to now n equals 2 as being our outer shell, and then 3, and then 4, and so on, it's just becoming larger and larger and larger. Okay, so we have to accommodate more electrons. Even though they all have the same number of valence electrons, overall they just have more electrons in their core. So because we're increasing our number of core electrons, that means we're just increasing the size of the atom itself. Okay, so our atomic radius is going to increase down a group. Our next trend with atomic radius concerns how we go from left to right across a period. So within a period, here's period 2, okay, the atomic radius decreases from left to right. So as I add on one more electron with each one, the nucleus is pulling those electrons closer to the nucleus itself, causing the radius to decrease. Now it's not a large difference, okay, because once you start to get into that outermost shell, all of the valence electrons are in the same shell. It's not as large of a difference, so we see that those atomic radii, especially for like nitrogen, oxygen, and fluorine, are very close to each other. So it's not a large trend or a large change in the trend like we see when we go down a group, okay, but once what's happening is as you're increasing the number of valence electrons, those are being pulled closer to our nucleus. Our next trend is ionization energy, or IE, and that is the minimum amount of energy required to remove an electron from an ion or from an atom in the gas phase. So ionization, we see the word ion in that. So this is literally creating an ion. Okay, ionization energy is the amount of energy needed to remove one electron. So I'm going to change this "and" to one electron, okay, from an atom in the gas phase. So the result is an ion, a chemical species that has a charge. We've talked about ions multiple times throughout our previous lessons, in our previous chapters. So here we have sodium. In its natural or in its gaseous state, it does not have a charge, meaning it has the same number of electrons and protons. And then as it ionizes, okay, we pull off one electron. So here's one electron that we've pulled off. It has 1 minus charge because it's just one electron, meaning our sodium now has a +1 charge. So we've created the sodium ion. And we're left with 1 electron. We can quantify our ionization energies, and those have units of kilojoules per mole. Okay, remember from our previous chapter that joules is a unit of energy, and we typically see it in kilojoules rather than in just joules because it's a lot of energy. So the amount of energy that it takes to pull off 1 electron is 495.8 kilojoules per mole. Now this is the first ionization energy of sodium. So it's, there's a space here that should say IE sub 1 is equal to 495.8 kilojoules per mole. Because that's the first ionization, that's the first electron that we can pull off. We can pull off more electrons after that, okay? That corresponds to then the second ionization energy and the third ionization energy and so on, okay? But when we're talking about the first ionization, it's talking about the most loosely attached electron. If you remember from sodium, sodium is in group 1, so it has 1 valence electron. So it's very easy to pull off that 1 valence electron. After we take off that 1 valence electron, all those electrons now are core electrons, and it's like a noble gas. Remember, when we're talking about noble gas core, we have core electrons. Okay, those are a lot harder to pull off because they're all paired up, they're nice and close to the nucleus, and they don't want to be removed. So with each subsequent ionization energy, we're going to see that it takes more and more energy to pull off more electrons. Okay, so what is the trend across the periodic table? Well, the first ionization energy is going to increase from left to right across a period. So we see an increase in that ionization energy from here to there, from left to right. So we have lithium, that's at 520. So again, that's in group 1. So it has 1 valence electron. It's sitting in an s orbital by itself, right? So this is lithium, this is 1s2, 2s1. If we show that orbital diagram, it just has 1 electron in a box right there, and it's a lot easier to pull off that electron. If we go to beryllium, that's much higher. Okay, so that was lithium. If we look at beryllium, that's 1s2, 2s2. Now I have 2 electrons. Now they're paired up, and remember, electrons would rather be paired. Okay, so they're paired up. It's a lot harder to take off that one of those electrons now that they're paired up and spinning oppositely. And then as we go further and further down, it's the same concept as we get now into our p orbitals. Okay, if we have 1 electron, it's a lot easier to pull off that 1 electron. But as I create more and more electrons that are paired up, so here's fluorine, okay, it's a lot harder to pull off those individual electrons. Then if I go to neon, we're talking about a full p orbital, full p shell, so all of those electrons are paired up, so its ionization energy is really high. So once we get to the end of a period, all of the electrons in that shell are paired up, and they don't want to be removed. Okay, so it takes a lot more energy for those electrons to be removed. So when you're thinking about ionization energy, it's very useful to draw out the electron configuration and the orbital diagram and look at what electron is being removed, and would it take more or less energy to remove that electron? Would it be more favorable to remove an electron because it's only one by itself in an orbital? Would it be a lot harder because more of them are paired up? Those are the things you have to think about with ionization energy. Now there are a few exceptions based on where some of these electrons are, which I believe is on my next slide, but I'll talk about it here. So if we look at beryllium and boron, I'm going to pull these over here. So we said beryllium is 1s2, 2s2, so its valence shell has those 2 electrons, so that's beryllium. If we do boron, we have 1s2, 2s2, 2p1, So its valence shell is now a 2s and a 2p. Okay, so, but there's only one electron in that 2p. Okay, so this one electron here is a lot easier to remove. So this electron is a lot easier to remove compared to, say, this electron here. Okay, because these electrons are paired and in a filled shell, whereas this electron is unpaired and in an unfilled shell. So boron, it would be more energetically favorable to remove this electron so that you're just left with those two electrons paired up in the 2s orbital. So if we look at what the ionization energies are, beryllium and boron, boron's is a little bit lower because of that one unpaired p electron. So it's a lot easier to pull off that p. And we see that trend throughout here, right? Each of these, they're generally either really close to each other or one's higher or one's lower. Okay, now a similar thing happens in nitrogen and oxygen for the same purpose, except now we have nitrogen, which has 2s2, 2p3, whereas oxygen has 2s2, 2p4. Okay, they change by one electron. Here, nitrogen has a half-filled p orbital, or half-filled p shell. Okay, and that makes nitrogen very happy. Whereas in oxygen now we have one of these electrons that could easily come out and be left with a half-filled shell. So this electron is a lot easier to remove because it's paired up and the p orbitals would rather be half-filled or whole-filled. So that's what we talked about in our previous lesson with those exceptions to our rules of electron configurations. Our shells would rather be half-filled or whole-filled. And while that moving of electron only happens in the s and the d orbital, which is what we talked about with our electron configurations previously, this is a case where electrons just prefer or are more energetically favorable in a half-filled or whole-filled shell, so that does change their ionization energy or the amount of energy that it takes to remove one of those electrons. Okay, so that's why we see this trend in nitrogen and oxygen where the ionization energy of oxygen is a lot lower than nitrogen because nitrogen has a half-filled p orbital, whereas oxygen has this extra electron compared to nitrogen that is easier to remove. Okay, so we see that also with phosphorus and sulfur, and then as we go down the periodic table, it gets closer together where those ionization energies are almost the same. Okay, so this trend is shown here, and this is an image from your textbook. So electrons that are paired are harder to remove than unpaired electrons, so the ionization energy changes. So we see that this is what we were talking about before, that electrons or elements and electrons in group 2A are harder to remove, whereas compared to 3A where we have that one unpaired p electron, that's what we were just talking about with beryllium and boron. Okay, so let's see, where do we see that? Lithium, here's beryllium, and then there's boron. Beryllium and boron. Okay, then our next one is nitrogen and oxygen. We also see that change, and you see it a lot through this trend. So we're going up and then we go down, then we go up, 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 then we go down, and those down portions are again in that, period, what is that, 5 to 6, or yeah, groups 5 and 6, and then also groups 2 and 3. Okay, so this is just prevalent in groups 2 to 3 and groups 5 to 6. Okay, so this is again just a the other oxygen-nitrogen example. So the electrons that lie in a half-filled shell with spins maximized, so that's our Hund's rule. We want to maximize our spin. They are harder to remove. Okay, so here's nitrogen, and here's oxygen, which again happens right there. So we see that change in ionization energy. So ionization energy does tend to increase as you go across the period, but there are exceptions due to where the electrons are and if they would prefer to be removed or not. Okay, so you have to keep that in mind. Okay, now the opposite of ionization energy is the trend of electron affinity. And electron affinity is the negative of the energy released when an atom in the gas phase accepts an electron. So we're now bringing in an electron instead of taking the electron out. So instead of removing the electron, we're adding the electron in. Okay, so it's the amount of, it's essentially how much does the atom want an electron. And this is where we have to remember our rule of 8. We would rather have, 8 electrons. 8 is great. We're going to talk about that a lot throughout this chapter and our next few chapters, why 8 is great. And it's because 8 is noble gas. Group 8 is noble gas. And those are our most stable elements. Okay, so as we get closer to our noble gases, that electron affinity is going to become a lot higher because we want to take on electrons to get to 8 electrons total. So, like ionization energy, electron affinity increases from left to right across a period because it's easier to add an electron as the positive charge of the nucleus increases. Okay, so as we add more protons, that increases our positive charge, meaning it's easier to take on an electron. So, we have fluorine, chlorine, bromine, iodine. They would love to take on one electron. So let's look at the orbital diagrams as to why. So let's look at fluorine. That's 1s2, 2s2, 2p5. Okay, so its orbital diagram is 1s2, 2s2, 2p5. Okay, so fluorine, chlorine, bromine, iodine, they all have this, s2p5 thing where they're missing one electron. They have 7 valence electrons and they want to get to 8. So they only need 1 electron to get to a full shell in the p orbital. So it's a lot easier to say, okay, I'm going to take on an electron and add it there. So they really want that extra electron to get a whole filled shell. Because remember, half filled and whole filled make our atoms happy. Okay, so we also have cases like, let's see, carbon, silicon, germanium, and tin. These are again similar to our exceptions before. So let's look at carbon. It has 1s2, 2s2, 2p2. Okay, so we have 1s2, 2s2, 2p2. And if we look at that, it's 1 electron away from being a half-filled shell. So its electron affinity is a lot higher in comparison to its surrounding elements, so boron and nitrogen. Okay, so this is boron, that's nitrogen, because it's 1 electron away from a half-filled shell, which again makes us happy. We like a half-filled shell and we like a whole-filled shell. So electron affinity does increase across a period, but there are exceptions to those rules because of how the electrons would be added and make a more energetically favorable orbital. So again, just like ionization energy, you may find it easier to draw out the orbital diagram and think what electron needs to be added, where would it be added to, would that give me a half-filled shell or a whole-filled shell, what would happen there, okay? So just think about where the electrons need to go for both ionization energy and electron affinity, but they have the same trend for the same but opposite reasons. Okay, so this is what we just talked about, the notable exceptions. So here's another example going into group 1 and 2. So this is, let's call it lithium and beryllium. So lithium has a higher electron affinity compared to beryllium because it has one electron that's unpaired. So it's a lot easier to add on an electron here and make a hole-filled s orbital. Whereas with beryllium, okay, and anything in group 2 really, it has a hole-filled s shell, okay, and if I wanted to add an electron, I would have to go into a p orbital, which is not as energetically favorable because it's higher in energy. So I wouldn't want to put that electron there. So my electron affinity is very low because I don't want the electron. Okay, so just think about where the electrons would be going and if that would be energetically favorable. Specifically, we want to maximize spin, half-filled, and whole-filled shells. Okay, and then this was the example I had with carbon. Okay, we added an electron compared to nitrogen. It's a similar thing there as well. So it happens for groups, let's see, groups 1 and 2, and groups 14 to 15, or 4A, 5A. So they're notable exceptions. They're particularly more prevalent higher in the periodic table. As you go lower down, like we saw with ionization energy, they don't change as much, but you do just have to think about where the electrons are going to be going. Is it easier or harder to add those electrons in order to maximize our spin and our whole and half-filled shells? Okay, so next up is the trend of metallic character. So metals tend to be shiny, lustrous, malleable, and ductile. Okay, so this is like, if you think of aluminum foil, that's aluminum, that's a metal. Okay, it's very easy to use aluminum foil, crunch it up, put it over your food before you put it in the fridge or whatever. Okay, so it's very shiny, it's very malleable. Okay, metals are also good conductors of heat and electricity. It's why we use them in wires in our homes and in our cords and everything like that. And they also have low ionization energies. Okay, they would rather form cations rather than anions. So it's really easy to remove those electrons. So we have to remember that our metals make up a majority of our periodic table. And in this periodic table, and as we've labeled them before, is everything that's labeled in green. So this whole kind of left side, center, and everything like that on our periodic table, these are all of our metals. So we have a lot of metals. So they all tend to be shiny, lustrous, malleable, ductile, conductors, and have low ionization energies in order to form their cations. So they would rather give up their electrons in order to form that cation. So they will happily give up those electrons, so their ionization energy is a lot lower. Next up, we have the character of nonmetals. So our nonmetals is everything in blue, which is not a lot of elements on our periodic table, but they do a lot of things. If you take organic chemistry, you'll see a lot of stuff with just carbon, nitrogen, and oxygen. That makes up an entire class right there. So even though there's not a lot of nonmetals, we do a lot with them. And nonmetals tend to vary in color. They're usually not very shiny. Okay, think of carbon. That's a good one to kind of think about. That's a classic nonmetal. This is like the lead in our pencils and stuff like that. Charcoal is a form of carbon. It's not very shiny. It's kind of dull and, brittle. They're not malleable in any way. If you think of like charcoal on a grill, it's very easy to crush those charcoals. They're also poor conductors of heat and electricity. Obviously, there's some exceptions to that, like carbon. And they also have very high electron affinities. So they want to form anions, so they want to take on electrons. Okay. Finally, we have the metalloids, which is everything in our little stair-step region here, everything labeled in orange. Those are our metalloids. And these are really intermediate. Their characters are kind of intermediate between both nonmetals and metals, so it kind of varies depending on what element you're talking about. And that concludes our section on periodic trends. Again, this section was mainly definitions and something we have to label our periodic tables with. The big kind of ideas that come out of this is thinking about where the electrons are going. So we started with atomic radius that changes with more electrons, how differing in our number of shells in our atom will change our atomic radius, and then the amount of energy that it takes to either remove an electron or add an electron to an element to either be more or less energetically favorable.